Hi everyone, my name is Matt. I'm a third-year chemical engineering major here at UCSB, and I'm working with the Gorman lab to deposit platinum nanostructures using microplasmas. So we're going to deposit these platinum nanostructures for fuel cells, for catalysts in fuel cells that are hydrogen-based. And a fuel cell produces electricity through electrochemical reactions. And this electrochemical reaction is hydrogen and oxygen reacting to form water. And here's the fuel cell. What happens is that hydrogen goes in at the anode and it becomes oxidized. The resulting protons get moved through the electrolyte to the cathode. And at the cathode, oxygen goes in and becomes becomes reduced. And this is the oxygen reduction reaction. And basically oxygen becomes reduced and there's a positive a cell potential that happens, and this is where the electricity comes from. And the thing is that the oxygen reduction reaction requires platinum as a catalyst because it needs to lower the activation energy to happen quicker. But platinum is an expensive metal, and in order to make the fuel cell more cost effective, platinum needs to be used more efficiently, and the two ways we're thinking about doing this is to increase the surface area of the platinum catalyst in order to increase the activity of the catalyst, and also to alloy platinum with other metals to decrease the amount of platinum in the catalyst to make it cheaper. And so our project goals for accomplishing this is we're going to utilize novel methods to deposit platinum nanoparticles for fuel cell catalysts. And we're going to be specifically using microplasmas, which I will tell you about on the next slide. We're going to explore how the plasma operating parameters affect the platinum deposition. We can change things like the pressure, the platinum precursor flux, the substrate type, and the electrical configuration. And depending on what we grow, we're going to characterize these platinum films and nanoparticle morphology using various microscopes. And we're going to investigate if platinum can then be alloyed with nickel, because if a platinum-nickel alloy is catalytically active for the oxidation reduction reaction and can be deposited directly, this is a surefire way to get the catalyst even cheaper. So what is a microplasma? A microplasma is a dense plasma confined to a very small space of about 10 micrometers to 1 millimeter. And looking here at the plasma column, it's confined by the walls of a capillary that has a diameter of about 1 millimeter. And looking at the cross section, these electrons are just bouncing off the walls very rapidly, which increases the ionization of these electrons in the molecules. And so the advantages to using a microplasma are that you can spray deposit nanostructured materials on any substrate, and you can grow particles to nanostructure/microstructured sizes. And you can also tune the particle composition, and you can use this to make alloys. And looking here at the view of an example of a molecule of silane, it enters the microplasma and it starts breaking down, where it then can nucleate. And what this means is that the silicon atoms come together and can grow and punch onto a substrate. And we hope to do this with platinum and nickel, in that the platinum and nickel atoms come together and punch onto a substrate. And so here's our microplasma deposition reactor. It begins with the inlet gases, because we flow these gases into the device top, which, looking at this image, they come in through here. One of the inlet gases is flown through the precursor cell, and what happens is at this precursor cell we can change the temperature for sublimation. So at higher temperatures we can get a higher saturation of the precursor of vapor. And our precursor is up here. It's platinum HVAC. We mainly use this one because by experimental analysis and literature, it's really good for the microplasma. And once we flow these gases into the device top, we use the DC generator to strike a high voltage discharge between the capillary and the stage, which is this purple beam right here. And this is the plasma beam, and we can use the stage to change the distance, which is delta D, here and here. And this changes the overall shape of the microplasma. And what happens is that this whole setup is inside the chamber, and we can vary the pressure of the chamber using the pump. And these are our control parameters that we change to change the platinum deposition. And what we can then do is characterize our samples. And we use, the first thing we use is what's called the scanning electron microscope. and this electron beam is shined onto our sample, where the electrons interact with the atoms on the sample and get scattered off, and this forms our image from the secondary electrons. What we then can do to get the composition is we can use an energy dispersive X-ray, or an EDX. And what happens is that when the same electron beam gets shined onto the sample, an inner shell electron gets kicked out of the atom. And what happens is an outer shell electron goes and drops a level and fills in that electron hole that was left by an inner shell electron that got kicked out. And once this drops a level, it releases a radiation energy, which is characteristic to each compound. So we would look for specific singular radiation energies that would come off of platinum to know that we're growing platinum. And the last thing that we use is an AFM, or atomic force microscope. And this is for our smaller samples, where we drag a cantilever along the surface of the sample and in an XYZ motion to get the surface topography. And so after growing our samples, we did various tests to understand the way the morphology changed with changing these parameters. And the first parameter that we changed was the substrate, and we grew on indium tin oxide and doped silicon. And what happened was that on indium tin oxide, we got the crystal faceted dense structures, and they're FCC platinum of FCC crystalline. And what that means is you kind of see these pyramid-like shapes on the top. And this is characteristic to platinum. This is what we would expect to grow for the crystal. But versus on silicon, we got this very porous deposit that ballistically aggregated. And what I mean by ballistic aggregation was that these clusters were shot onto the surface of the silicon and stuck and clumped on top of each other into these tree-like structures. And we can definitely tell that the substrate type affects the morphology. And we're identifying that the main reason for this is that the substrates are different in the sense of the way that they complete their current. And ITO sits on a very thin layer, is very thin, and it sits on a layer of insulating glass. Versus doped silicon, the circuit has to complete through the whole substrate. And we don't exactly understand why this changes the morphology, but we're identifying this as the main issue that's changing the main thing that's changing the two morphologies. And we're looking into it further. The next effect that we looked at was the pressure effect. We grew at lower pressures, like subatomic 50 torr pressures, to atmospheric, which is 760 torr. And at a lower pressure, we got a lower platinum precursor flux, which resulted in this thinner film. Versus at the higher pressures, which is what I showed you earlier, we got this aggregated clusters that were stuck together. And after growing, changing various parameters that I don't have time to show you all of them, but changing parameters and doing multiple depositions, we found that these samples are too big for nanostructures. And we were growing for too long and too close. And so what we decided to do was to move farther away, and we wanted to grow at atmospheric pressure. But at high pressures, the microplasma becomes unstable. And so what we had to do was add this new counter-electrode grid, which I'll show you on the next slide, that helped complete the circuit quicker. And so right here is the counter-electrode grid, and this is the microplasma. And it's shined onto the grid, and it's then able to complete the circuit to stabilize, since this grid is very close to the capillary. And then this is the picture of the grid. It's metallic with many holes to allow this thin beam to pass through and deposit material. And after inserting this and changing our setup and moving the stage farther away, we were able to grow nanoparticles. And so this image on the left is a silicon substrate that was treated with argon plasma that had no precursor. And this one on the right was a silicon substrate that was treated with argon plasma that had precursor. And our main reason for doing this one was it's our control, and we wanted to see if the microplasma jet affected the roughness at nanostructure size of the silicon. And then we decided to grow our material. And these yellow whitish dots are actually 4 to 5 nanometers. I know the scale is very hard to see, but it's 4 to 5 nanometers. And our average particle size here was 4 nanometers with a range of 3 to 10 nanometers. And this is what we wanted to grow. And the reason why we wanted to grow this size was that 4 to 5 nanometers particle size of platinum is the best size for a platinum catalyst, in the sense that it's the smallest size, so it has the maximum surface area, but it's not too small, because if you go smaller than 4 to 5 nanometers, you then make the nanoparticle unstable and it could lose its catalytic potential. So in summary, we deposited a diverse range of platinum nanostructures and morphologies. And after changing the parameters, we were able to see that pressure and the capillary substrate distance had the greatest effect on platinum morphology. And then we were able to achieve an average platinum nanoparticle size of 4 nanometers. And based on this information, our next steps are then to try the platinum nickel alloy synthesis, since nickel is readily available and less expensive than platinum. And we wanted to test if platinum nickel is catalytically active for the oxidation reduction reaction, and we're going to do this through electrocatalytic testing, which is currently underway. And I just wanted to thank my professor, Professor Michael Gordon, for allowing me into his lab and really taking me under his wing and teaching me about microplasmas. And I wanted to thank the PhD students, Joffrey Bonneton from Belgium and Catherine Mackey, because they worked alongside me in the lab and they were very instructional and very helpful. And I wanted to thank the Gorman Scholars Program for funding my research. Thank you.